Hey guys, Ms. Subin here, and today we're going to be solving equations with square roots. So today we're going to look at two-step equations where the unknown number is being solved by taking the square root. So for example, we have x squared plus 2 equals 11. We're still going to be looking for the value of x, just one of the steps is going to be different than what we're used to. So the idea that we're going to be using here is that if any number is being brought up to the power of 2, we can take the square root and we're left with the original number. So an example of this would be 5 squared, but taking the square root of that. So the square root of 5 squared, that's how we would read that. So the square root of 5 squared, well, 5 squared is 5 times 5, which is 25. So the 5 squared is 25, so that means we're taking the square root of 25. And the square root of 25, well, 25 is a perfect square, so when we take the square root, we're left with just 5. Same thing with this one. We have 7 squared, the square root of 7 squared. Well, 7 squared would be 7 times 7, which is 49. So instead of taking the square root of 7 squared, we're taking the square root of 49. And the square root of 49, because 7 times 7 is 49, the square root of 49 is 7. With these examples, you should be seeing that the number that we start with and the number that we end with are the same. So basically, if you see a square root, which is this symbol, and a square, or a power of 2, you can just kind of cross them off and keep the number on the inside. So over here, because we had that square root and we had the squared, we can just keep the number on the inside, and that's going to be our answer. We can use this idea for when the number on the inside is something we do not know. So let's go ahead and try some examples. So here's just one-step examples. X squared equals 36. So if x squared equals 36, what I can do is I can choose, instead of dividing both sides or adding to both sides, I'm going to take the square root of each side. Because I'm doing the same thing to both sides, we're going to stay balanced on both sides of our equation. Well, we saw on the last slide, if we square a number and take the square root, they cancel, and we're just left with a number on the inside. I don't know what x is, but if I multiply it by itself and then take the square root, it's just going to be x. And 36 is a perfect square. 6 times 6 is 36, so the square root of 36 is 6. Let's try another one. So x squared equals 16. What I can do here, again, both sides of the equations, as long as I do the same thing on both sides the proper way, then we should be good. So I'm going to take the square root of each piece. Well, if I'm taking the square root and I'm squaring something, those cancel out each other. It's kind of like multiplying by 2 and dividing by 2. We just don't know what x is, so we don't know what we're multiplying and dividing by, but they cancel out. And I'm left with just the number on the inside, which is that unknown x. And then the square root of 16. 16 is a perfect square, so it's going to be 4. 4 squared equals 16. So I picked some pretty easy examples there because we had perfect squares. This can be done with non-perfect squares. We just have to use our model from yesterday. So I am going to, I am going to take my pen. We're going to find the middle of our equation. And I'm still going to take the square root, but you'll see in this example it's going to be a little bit more complicated because the square root of x squared is going to be x because those square root and the squared cancel. And the square root of 12, well, 12 is not a perfect square, so we're not going to get a whole number for our answer here. Because 3 times 3 equals 9 and 4 times 4 equals 16, 12 is somewhere in between these two numbers. So that means our answer is going to be somewhere between the whole number 3 and the whole number 4. We can get a better approximation by using our model. So for the square root of 12, I'm going to draw the square that's a little too small, which would be a 3 by 3 square. Because 3 times 3 is 9. Then I'm going to make my model a little bit taller and a little bit wider. And I'm going to write a fraction for my answer. So my whole number is 3, and then for my fraction, out of the new 1, 2, 3, 4, 5, 6, 7, I need to get to 12. So 9, 10, 11, 12. We use 3 out of these 7. So x is going to be about 3 point something. And we get that point something by using our calculator. Let me get my calculator out. So 3 divided by 7, because 3/7, gives me a crazy decimal, but because we're approximating, we're just going to use 3.4. We're not going to round just the first number after the decimal. All right, so let's try another one. So here we have x squared equals 20. Since we're squaring the number, what we're going to do, we're going to find the middle, and we're going to take the square root of each side. So x squared, what I'm going to do, because we're square root and squaring, we're left with just the number on the inside, which here is that unknown x. And then 20 is not a perfect square, so we're going to have to think through this. 4 times 4 is 16, which is too small for the square root of 20. And then 5 times 5 is 25. So 16 and 25, in between 16 and 25 is where we would find 20. So I'm going to draw my model using a 4 by 4 square and then make it bigger. So my 4 by 4 square, I have 1, 2, 3, 4, 1, 2, 3, 4. Because 4 times 4 is 16. So my whole number is going to be 4. Then I can make my model a little bit taller and a little bit wider and use a fraction to represent how much that new space we need. Here I see 1, 2, 3, 4, 5, 6, 7, 8, 9 new boxes. Out of the 9 new boxes, I need to get to 20, 16, 17, 18, 19, 20. I need 1, 2, 3, 4 of those 9 boxes. Finally, I want you to write that as a decimal. We get x is equal to 4 point, using my calculator, 4/9, 4 divided by 9. It's 0.4 repeating. We're just going to use that 4.4. All right, so those were both one-step examples. There are two-step examples that we're going to be seeing today. For two-step examples, we're going to do the same steps, except for there's one thing we have to do before we can take the square root. Before we can take the square root, we're going to split our equation in half, and we need to get the variable term by itself. So because we're adding 4 to x squared, we also need to subtract 4 from both sides. So this should feel the same as when we're solving two-step equations normally. The x squared stays the same, and 29 minus 4 is 25. Now that we have that x squared by itself, instead of dividing like we normally do, we're going to take the square root of both sides. Well, the square root of x squared is just going to be x, and the square root of 25, because 5 times 5 is exactly 25, we're going to use the whole number 5 for this answer. Then we have x squared minus 3 equals 33. I'm going to do the same thing. Find the middle of my equation, find the variable term. The variable term is not by itself, so we can't divide by taking the square root. So instead, I'm going to get rid of this minus 3 by also adding 3, putting us back at our starting value of x squared. Well, x squared minus 3 plus 3 is just going to be x squared, or just x squared, yep. And I'm left with 33 plus 3, which is 36. Since it's x squared, I'm going to divide by taking the square root. The square root of x squared is just x. And because 6 times 6 is exactly 36, our answer is the whole number 6. All right, let's try just one more example, or one more set. So for these ones, we're going to be combining both two-step, and we're going to be working with non-perfect squares. On this first one, x squared plus 2 equals 16. Even though 16 is a perfect square, before we can start solving, we need to get the variable term by itself. So I'm going to subtract 2 from both sides. That leaves me with just x squared, because the 2's cancel, positive and negative 2 cancel, and 16 minus 2 is 14. Now that we have x squared, we can divide by taking the square root. Well, the square root of x squared is just x. And the square root of 14, we're going to have to draw a model. So perfect squares that are close to 14 would be 3 times 3 equals 9, and 4 times 4 equals 16. 14 is going to be somewhere in the middle of these, so we're going to draw a 3 by 3 box and make it a little bit bigger. So here's my 3 by 3. 3 times 3 equals 9. Okay, so 3 is our whole number. Make our model a little bit taller and a little bit wider. Use a fraction to represent how much we need to get to 14. So here we have 1, 2, 3, 4, 5, 6, 7 total. To get to 14 from 9, we need 9, 10, 11, 12, 13, 14. We use 1, 2, 3, 4, 5 boxes. To write that as a decimal, I'm going to use 3 as my whole number, and then in my calculator, I'm going to do 5 divided by 7, which gives me a crazy decimal, but I'm just going to use the first number after the decimal to make it 3.7. That means about 3.7 times 3.7 equals 14. All right, one last example that we're going to be doing together. We have x squared minus 5 equals 14. So I'm going to find the two sides of my equation. And I need to get the variable term by itself, so I'm going to add 5 to both sides. Well, x squared minus 5 plus 5 is just x squared. And 14 plus 5 is 19. The square root is what we're going to take next. We'll divide by taking the square root, because the square root of x squared is just x. The square root of 19. Since 19 is not a perfect square, we're going to have to use a model. Well, 4 times 4 is 16, and 5 times 5 is 25. So that means 19 is going to be somewhere in the middle. So I'm going to draw a 4 by 4 square to start off with. So our 4 by 4 square, I'm left with 4 times 4 is 16, which means our whole number is going to be 4. For a fraction, we're going to make our model a little bit taller and a little bit wider. We have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. To get to 19 from 16, 17, 18, 19, we use 3 out of the 9. So for our final answer, we keep the whole number 4, and then 3 divided by 9 is 0.3 repeating. We're just going to use 4.3. Please take your time. You can rewatch any parts of the video, but at this point you can go ahead and start the lesson.